Michal, you know, from Prague, but spending the year at Dymax every, a lot happened since the original brief, I think.
Yeah, so well, thank you everyone for coming, and thanks for the invitation. So it's actually great to be here actually for you. So I want to tell you actually stuff which I'm kind of excited about for the past couple of years. And today I want to actually tell you something about the work which we did with my student Sudata. She's in Prague and Mike, who is here at Rutgers. And it's going to be about decomposition of strings at a distance and sketching. So I will try to go slowly, and my goal is not to like give you all details of everything. I will just like more expose you to some of the ideas. So if you can like zoom out for a while, and then you can like kind of zoom in again, and you will actually, I think you will be able to catch up. So let me start actually. What is our goal? So we have the following problem. So we have two strings, X and Y, and they are over some finite alphabet. Over here, this would be like English letters, and you want to compare them. So you want to check whether are they equal or are they similar, and how similar are they? So you want to measure these kind of things. And of course, the question is, how do you measure this? So if you look on these strings, they look somewhat similar, and depends on how we are going to measure it. And so that's what we are interested in here. And one possible way, the simplest way, is to just measure Hamming distance. So I have these two strings, and I measure how many symbols actually differ in the two strings. So I just align them left to right, and that's the measure of dissimilarity or similarity. So I measure how many substitutions I have to make. So over here, I have to make 4 substitutions, and I get the other string. So I go from X to Y. And so I measure the number of bit flips. Well, I usually actually think of the length of the string as being n. Well, this is just a coincidence. Sorry about that. So the length of the strings is n for me, and usually I think that they are actually of the same size. So I don't, we could actually adapt it a little bit to different sizes, but depends. So, but Hamming distance is actually not a good measure to measure similarity of strings, because if you look on these two strings, A, B, A, B, A, B, A, B, and this is B, A, B, A, B, A, B, A, B, clearly they are almost the same. Actually, if you remove the first letter in this one and say the last one in the other string, you get the same thing, but the Hamming distance is huge, it's n. So n is basically the upper bound on the Hamming distance. You can do worse. And so this Hamming distance doesn't capture kind of like our notion of similarity. So a natural measure actually is other measure, and that's at a distance. And that's the focus of this talk. So in edit distance, you actually allow edit operations. So edit operations, by that we mean actually like a bit flips as before. So you can actually change W to G for cost of 1. But you can also remove symbols, and you can insert new symbols. So for example, over here, I am removing Z. So the Z disappears from Y, and I am inserting J in X, and I get Y. So I measure how many these individual operations I have to perform to X to get to Y. And it turns out that it's actually symmetric. So, the picture somehow suggests that you can go the other way and you get exactly the same number. So this is actually a distance measure. And it gives you metrics on the space of strings. So we would like to compute this. And that's kind of the first initial thing we would like to do. So just compute this. So I will tell you how you can compute it, what we know about that. And so why do we actually care? Well, it turns out that this is actually very useful in many contexts, like when you are processing like text, like, you do some changes to your next paper for Fox, and then your friend does some changes, and then you want to compare who did actually more work. So this is actually like a possible measure. But actually also this is actually very useful for comparing like DNA sequences and proteins. So it actually can basically like tell you which strings are closer together, which proteins are like more similar. So it actually people can classify species based on that. So it's actually useful. And when people want to compute it, so DNA sequence can take like 10 to the 9 symbols. So it's actually the strings are like sizable. So you would like to do it fast.
Is it true in biology that insertions and deletions and switches are the same, or roughly the same cost or frequency?
Well, actually, in biology, it's more complicated. So it's not actually true that like every symbol has the same probability of like switching to other symbols. And sometimes you may actually also allow like moves of the whole block, which may happen like when you have a cross crossover. So it's actually more complicated, but this is the basic setup, right? So this measure is actually also kind of like a dual. The one which I just showed you is dual to just measuring longest common subsequence of two strings. So if you basically just pick up if you just pick up the longest common subsequence of the two strings, it doesn't have to be continuous. Then it basically like what you are left is this matching, the largest non-crossing matching between the two strings, where you match the same symbols, the same characters. And it's dual. So if I would just allow like insertions and deletions, it's exactly dual. So n minus this is going to give you the other one. So this is also like a well-known problem, and it's basically the same thing. Although like for some applications, it's problematic because, for example, if you want to approximate it, and then you get into problems. What are you approximating? So it's the same thing. Yeah.
The answer of the edit distance is not exactly the minus matching.
Right.
Like there's some like two approximation maybe. I mean.
Well, there is a formula, so it's like n minus this thing actually gives you, and maybe you have to divide by 2. So you're right. But if I don't allow substitution, so if I would count this as a deletion and insertion, then it's like exactly the same. So there are actually various variants of this edit distance. So the vanilla thing which I described is Levenshtein distance, sometimes called. There is Ulam distance, which basically assumes that every symbol appears just once. We have large alphabet. Basically, we are comparing somehow permutations or like permutations restricted to some subset. Or you can actually allow the whole moves of like whole block of symbols for one. But I'm going to focus on the first line, so that's what people usually focus on. So we want to compute it. So what can we actually say about computation of edit distance? And there is actually a lot of work being done on that, and started already in the 70s. And it's interesting because people like started it in biology. So like the first algorithm, so they basically was from biologists. So they came up with an algorithm to compute it. And that algorithm runs in time n squared. And over this past 50 years or so, the best we can kind of actually do is like shave off like log square from that time. So it's actually we were not able to improve that algorithm much, except for logarithmic factor. But there are some other algorithms. There is Buchanan's 85 algorithm, which runs in time kn. And this parameter k is actually going to be important throughout my talk. So by k, actually, I mean either the edit distance on some upper bound of the edit distance. So the actual edit distance, if the actual edit distance of the two strings is k, of the string x and y, then the Buchanan's algorithm runs in time kn. And that's actually very simple, like a very simple observation on the basic algorithm. And you can actually do somewhat more fancy algorithm, and that actually runs in time n plus k squared. So in particular, if the distance is small, like like square of n, then it actually runs very efficiently. It's linear time algorithm. So that sounds pretty good. So throughout this talk, actually, what I will be eventually interested in is in this what I call threshold k edit distance. So I'm giving this parameter k as parameter to the algorithm, and if the edit distance of the two strings is below k, I want to compute it exactly. And if it's above k, I just have to say, well, it's too big. So that's kind of like the game I'm actually going to play later. So for most things, if you just take two random strings, they will actually differ a lot. So the typical edit distance will be actually linear, but it makes sense to look when the edit distance is not too big. So these are results which actually appear over like long period of time. And then in 2015, there was actually breakthrough result by Bakurs and Indik, and they actually show that you cannot really do much better. So these algorithms are basically optimal. So So this n plus k squared, you cannot improve it except maybe shading some extra logs. And that's, so there is a good reason. And this is under the strong exponential time hypothesis. So I will actually show you in a minute what actually it says. So, so how does actually computing any distance work? So if you have never seen it, it's actually very simple. So this is an example of a so-called dynamic programming algorithm. But what you are really trying to do, you are trying to match these two strings together. So there is like simple recursive way how to do that. So you say you take x in the middle, and then you start to actually see like how to match it to various subdivisions. So you try this subdivision of y, then you switch to this one, and you switch to this one. So you try all possible subdivisions of y with respect to the middle x. And for each subdivision, you basically like figure out what's the best way to match these two substrings. And actually they don't interact together. So like the optimal solution on this side and together with the optimal solution on that side actually can give you the optimal on both sides. You just basically just maximize, minimize what is the minimal at a distance. So this is very simple algorithm, and there is at most like n squared times n squared different subproblems. Each subproblem takes you n, so that would give you time n to the 5 if you implemented this naively. But you can actually do it in quadratic time, if you just evaluate the pieces in right order. So this is the standard algorithm, and as you can see, somehow embedded in there is this search, this quadratic search, where we're trying to actually match various like single piece to all other pieces at the bottom, and that is actually the basis for this reduction between strong exponential time hypothesis and improving this algorithm. So in particular, what Bakurs and they showed is that they basically show that if you have an algorithm for any distance which runs in time n to the 2 minus epsilon for some epsilon constant, then you can actually get the algorithm for SAT, which runs in time 2 to the 1 minus delta n. So SAT is satisfiability, formula satisfiability. And it turns out that many people are trying to actually improve this algorithm, and we don't know how to do that. So there is even conjecture that you cannot do that. And so assuming that conjecture, which is called strong exponential time hypothesis, you cannot actually improve this algorithm. So this n quadratic algorithm is actually optimal under this. So I really like this. So this is actually fine-grained complexity, because this is a subfield now of complexity, which is called fine-grained complexity, because it actually relates algorithms which are running in polynomial time to algorithms which actually run in exponential time. So you may just wonder how this can be happen. And there is basically a reduction which reduces SAT instances into eddy distance instances. So if you can solve eddy distance instances fast, then you can solve also SAT instances fast. And the reduction kind of like has to do exponential blow up. So you start with some formula phi on n variables, and you reduce it to eddy distance instance of length to the n-half. So you have basically this exponential long string. And the string x and y, basically they consist of like small blocks, and each block basically corresponds to partial assignments of these n variables. So like first half, second half. So that's why you have 2 to the n. And the point is like there is some clever encoding, so that if you have two assignments actually are satisfying the formula, you get like small eddy distance. And if none of them, then you get all the eddy distance are big. So you somehow like if you combine it in the right way, what you get is that if the formula is satisfied, but there is this good match which brings down the eddy distance, and otherwise the eddy distance is large. So you can kind of distinguish whether there is satisfiability. And that kind of goes to this quadratic search in the algorithm. Yeah.
Does this also translate to an approximate version?
Not. It does not. This has to be really like the difference between the eddy distance is really tiny, like 1 basically. So it does not actually. And so there are some results on approximation, and I will get to on my next slide. But so this is so there are some slight improvements on this result. Like you cannot shave even like polylog factors unless you prove some circuit level bounds. So approximating eddy distance. So that's a very good question. So there was actually like, since there wasn't progress on exact computation for many years, people started to look at approximating at a distance. And you can take this n plus k squared algorithm, and that you can use it as like very weak approximation. It will give you like square root of n loss, like inaccuracy. So that would be kind of like the first approximating algorithm. Then there was a polylog algorithm, approximation algorithm. So I'm speaking of multiplicative factors. You get output which is within like a polylog factor from the optimal. So that's actually, that was done by Androni, Krautkammer, and Onak in 2010. And then in 2018, actually we managed to show basically design algorithm which gives you like constant factor approximation in time n to the 1.64 whatever, and there was some follow-up work, and eventually actually Androni and Nosacki in 2020 they got constant factor approximation which runs in time n to the 1 plus epsilon. So the approximation actually this O1 depends on epsilon, and the dependence is really bad. It's like doubly exponential. And we don't know whether you can do like 1 plus epsilon approximation in subquadratic time. So that's still actually open. Well, there is some, as I said, there is some small result, small in the term of this. So you can approximate like to 1 plus 1 over polylog unless something happens. So there are some bounds on approximation. So what we would like to get, so in general, like one would get like algorithms which give you 1 plus epsilon approximation in a multiplicative factor, but we are far from that. So the best you can actually get using these techniques seems to be like 3, approximation factor 3. Okay, so that's about at a distance and computing at a distance. So let me a little bit switch gears and let's, let me give you actually, before I switch the gears, let me give you a very simple approximation algorithm, which I hope you will like also. So this is an algorithm by Saha in 2014, and it's a greedy algorithm. So let's actually, I got these two strings, so I'm going to just greedily build the matching. So I start and these symbols match, so I'm just happy and I match them because that's actually the best thing you can do. And now I run into a string, into two symbols which actually differ, Z and T. So what should I do? So I need, so let's say I'm just trying to either insert or delete symbols, so I don't allow substitutions, and we don't know what to do. So if we don't know what to do, the best thing is just to flip a coin. So you just flip a coin and you just remove one at random. And we were lucky, so we actually removed the right symbol. And we continue actually with the greedy matching. Now we hit these two symbols, and so we have to remove one of them at random. So we remove G again, like this doesn't work, so we remove H. And okay, so now it still doesn't work, but now we actually remove W. We decide to remove W, and now we are lucky. We removed H, and now we actually continue. And again, there's for J. So like this, we can actually construct optimal matching. So the algorithm is actually very simple. You just basically scan the two strings left to right. On every mismatch, you just flip a coin, which symbol to preserve, and you draw out the error. Turns out that this actually works surprisingly well. So this gives you a matching of size somewhere between n minus 20k squared, where k is the real eddy distance, and n minus k. So it's like k approximation to eddy distance. And the time is linear, so it's just so that
because of a random walk on the line, basically.
Exactly. Right. If you analyze it, so the analysis is tricky, but not hard. It's basically a random walk on line. You basically like what you are doing, you are trying to synchronize with the true optimal matching, and that like at each step whenever you hit a mismatch, you are like off the optimal matching, so you have to decide whether to go left to right. And if you analyze it, then that's where this comes from. Of course, you may ask a question: can we do better with some other distribution? And because this half-half distribution, maybe you can like count how many symbols we erased lately from left, how many from right. And actually, the answer is no. So this is pretty much optimal, and that's what we have shown with the paper in Mike like last year in Soda. But we also found a deterministic rule how to delete the symbol. So we can actually get away with the randomness. And the deterministic rule is actually very simple. It basically tells you from which string you should delete next. So first time we run into a mismatch, we delete from X. Now the next 3 mismatches we will be deleting from Y. Then we will be deleting 5 from X, etc. And you get actually alignment of size between n minus k squared and n minus k. Why this works? Well, because basically when you are deleting from like the same string, you basically are kind of like scanning and trying different slopes for alignment, and you should hit it actually. You know, if there are not that many, then you will hit it and you will stick to it until there is a mismatch, and then you do again like basically this search for the optimal alignment. So you can actually randomize it very nicely. So Barna Saha used it actually to solve a more general problem. So she was solving some Dick edit distance problem, which is problem about actually balanced parentheses strings. You know, like in compiling when you are compiling program, you want actually or LaTeX, you know, everything should the parentheses should match, and that's a more general problem. So we can solve that there. So I will actually get back to this algorithm later, not the deterministic version, but Barna's version. But if you actually think about the problem, what we are trying to do, what in reality happens is that we don't have just 2 strings, but we have actually like whole databases of strings. Like we have like database of DNA sequences. I give you, and I want to actually compare all of them because I want to build maybe phylogenetic tree, which means I have to actually figure out who is closest to whom, and then based on that, I'm building some tree. So in general, we have actually multiple strings, and we want to compute actually at a distance of every pair of the strings. So you know, so I want to compare the distance between Y and U and W, etc. So that's really like what we would like to do, because that's what really people need. So in this setup, we actually allow some kind of pre-processing. So I actually each string X, Y, Z, I can independently pre-process in some digest, and from that digest, I may want to actually compute at a distance. So like over here, from the digest, I would like to efficiently compute YZ, the edit distance of YZ, the edit distance of XZ, etc. So that is basically like general problem we would like to solve.
The proximity preserving hashing works only for Hamming distance.
So it works a little bit here also. So there are some works in here, but yeah.
Okay, you will get there. Okay.
Yeah. Well, I'm not getting there, but
You won't get there. Okay.
let me just shave this under the carpet. So that's not where I'm heading. So
It's worth mentioning that there is something like this. I mean, hashing in general should put things apart from each other as much as possible. That's what we associate with hashing. But there are hashing schemes which actually put things that are similar close to each other. It's pretty magical, I think.
Right.
It's worth knowing about.
Yeah. All right. So right. Okay. So this actually this program, the way it's actually stated. So there was a result by Alexander Goldberg, Rubinstein, and Saha, which basically like takes pre-processing time per string like a linear, and then each edit distance, each pair of edit distances can be then computed in times k squared. And it's basically based on this algorithm n plus k squared algorithm, which where you basically do the pre-processing and not through digest, and then you do the actual computation.
How long are the digests?
Right. So they are actually linear because you have to prepare basically like you have to prepare a hash table for every substring of your string. So the digests actually over here are actually linear size, and that's the issue. So sometimes actually you would like the digest to be short, because if you have a lot of strings, you want actually to store them in memory. So ideally, you would like to have like small digest, and we usually call that sketch. So over here, now we got to this edit distance sketches. So my goal now is to basically calculate a sketch, and by sketch I mean something short. And from that sketch, I would like to actually derive at a distance. So I take X, I process it into some short sketch, maybe using randomness. So I'm allowing to use randomness. And then I do the same thing for Y, and then maybe for other things. And then from the sketches, I want to actually compute the edit distance. And the question is, what is the length of these sketches which we need, and what can be done? So the goal is to actually minimize this sketch. Of course, there are like various ways how what do I mean by computing the edit distance? So either I mean actually compute it exactly, like say in this threshold k edit distance, where I have this threshold k and I should give you exact number below some threshold, and then everything else is just too big. Or like do I want approximation? So ideally you would like to have a sketch which gives you 1 plus epsilon approximation. So we know how to solve this problem efficiently. We don't know how to solve this approximate edit distance problem at all. So we don't know like, and well, we have something. I will show you something is known, but it's not stellar. So what I will show you today is in the later part of the talk, I will actually show you a solution for threshold k edit distance, which gives you this sketch size of roughly k times 2 to the square root of log n log n. So this is a weird function. We will see it like a couple of times, but it's a time function which people now are, I guess, getting used to. It's sitting somewhere between polylogarithm and sub-polynomial. So it's actually growing slower than any polynomial, like quadrat, like square root of n or cube root of n. It's growing slower, but it's growing faster than log n to the 10 and stuff. And yeah, so that's what we get. So we are kind of thinking of this as like negligible, and the point is that it is just linear dependence on k, which is actually required. So it's known that if you want to compute the distance exactly, you need sketch of size at least k. So let me actually just switch gears and let's go back to Hamming distance for a second. So you can actually ask the same problem about Hamming distance, and I want to actually threshold k Hamming distance sketch. So what that means, I give you two strings x and y. I want to compute some sketch from them, so that if x and y actually differ in at most k places, I wanna actually say what is their Hamming distance, and if they differ more, I just say it's too big. So can we do that? I guess there is a spoiler on the slide. So all right, so you can so let's say that we take some systematic linear error correcting code which can correct up to k errors. So systematic means that if I take a code word, so if I make a code word of x and y basically stays, and there are some extra parity bits. So that's exactly what Pravesh was talking the other day about, like the locally decodable codes. So this is so you compute so you take a good code which is systematic, so it preserves the message and it's linear, so that's important. And what's going to be my sketch? So my sketch is going to be these parity bits. So that's going to be my sketch. And you can like easily calculate that the size of these parity bits, if you want to correct k errors, has to be about k log n, and that's basically optimal. You cannot do better. So this sketch is linear size essentially, except for logarithmic factors. And so how do I evaluate two sketches? So if I give you two sketches, how do you calculate the Hamming distance? Well, we just create the following word of them. So I take 0 to the n, and I append the difference between parity x and parity y. And by this I mean you take the code is linear, so this is some vector, so you just subtract the two vectors, so like coordinate wise. So that's what I'm going to create, and now I just run error correction on this. So if I run error correction, if I would start it from x minus y, so if I would actually take code words for x minus y, which is again like some string over my alphabet, then x minus y would actually exactly have the the parity bits would actually correspond to parity x minus parity y because the code is linear. So x minus y, so basically like but what is x minus y? Well, x minus y in coordinates where x and y actually are the same, you get 0. And in the coordinates where they differ, which is the most k coordinates for us, there should be something non-zero. So if we start from the 0 to the n, actually exactly we can recover the exact places where these errors are. So not only that we recover not only that we recover how many they are, but we actually know where they are. And this is actually turns out to be useful. So we will actually need that later. This ability. So if I so actually for Hamming, all these problems are trivial. So computing Hamming distance of two strings, that's just you just zip through them and you know what the distance is. It's easy to sketch, and there are basically just standard dimension reduction tools. Actually, basically you can sketch to polylogarithmic size and get good approximation. And but for edit distance, this seems to be much harder, and we don't know much about it. So for this threshold k edit distance, it is surprising that it's actually possible at all with some good dependence on k. And the first result was actually by Belajogi and Zhang in 2016, and that was actually surprising that you can actually do anything. So I was surprised. And they gave us a sketch of size k to the 8. That was a few years later, it was improved by Yen, Nelson, and Wu to k cubed. And then Kotsuyama, Kaporot, and Staikovskaya gave this k squared sketch. And now what I'm basically going to show you, I will show you tools for actually doing k squared. So this is from the work with Sudata from last year in Stock, and this is actually upcutting paper in Stock with Mike. So we kind of push it farther. So that's what I'm going to do. But before getting there, let's kind of be even more greedy. So far we were talking about sketch, and the question is how complicated it is to actually calculate from the sketch the edit distance. And none of the results actually tell you how complex it is, but it's actually fairly complex. So it's like polynomial in k, typically. In all these guys, you have to do polynomial computation to get the edit distance. And the question is, can you kind of do it faster? So you would like to be more greedy, so you would like this procedure to be really efficient. And the most efficient you would actually hope for in general would be to get actually some kind of embedding of edit distance into Hamming distance, or L1 node. So I would like some magic function f, which takes a string and maps it to some other string, maybe over some other alphabet, I don't care. And it will take a string y and map it to some string. And magically, the edit distance of x and y will translate into Hamming distance of fx and f1. Yeah.
So I think I'm missing something. When you're sketching the edit distance, is it exact, or is it are there approximation factors or what?
So on this picture, it's actually exact up to the threshold k. Once you are at the threshold k, we just say it's too big. Yeah. Otherwise, it's actually over here. You just want approximation. So I just want that the Hamming distance roughly corresponds to the edit distance up to some scaling, which is called distortion, and there may be it's in some multiplicative range around the Hamming distance, and that's basically the distortion. So basically, you would like to translate edit distance into Hamming distance, and that's seems to be tall order. So there are actually very few results on this, and somehow if I jump in the middle. So the best result, actually, which we know of, which is this Ostrovsky-Rabani result, which does this embedding of edit distance into Hamming distance, and it has a distortion 2 to the square of log n times log n. So this term 2 to the order log n or log n square is actually exactly the same term which I have shown you in our embedding. And in particular, if you would actually improve their embedding, the distortion for their embedding, you would actually get better result, like a black box out of the box. So that is you know, that's really an interesting problem, and I think that's really like a very interesting problem.
So wait, why is not direct reduction given the result? Why don't you map edit distance to Hamming distance and run the parity check as before?
You mean for theirs?
Yeah.
You can, but then you will get this distortion. So it's going to be solving the approximation. Right. You can do that, and you are solving approximation.
But
right.
you got the exact.
Right.
Yeah, so you only want an approximation. They could have written this as a corollary.
Right. So they do have actually, they basically give you like approximation, exactly. So that are the only approximation we actually know. So there are some, but so I'm saying, you know, I'm kind of playing both ways. So I'm saying this number is small, but at the same time, it's actually big. So,
Is it convenient for you?
right. So, but usually, like, you know, you would like actually approximation factor, which is like 1 plus epsilon ideally, because that would be really actually practical. You know, like astronomical constants doesn't actually work either.
This distortion, what is the length of the new string?
So they have actually deterministic one where the length is kind of like quasi polynomial, but you can make it randomized, and then you get actually polynomial, or you can basically make like linear size pretty much. So you basically the strings you get from this embedding, you basically can make it linear size.
But you can always like sketch the L1 norm into polylog dimensions or something.
Right. So like once you are here, then you can like sketch it to smaller. So if you allow randomness, then right.
Are there lower bounds against the distortion?
So exactly there are lower bounds against the distortion. So there's a lower bound, like the best lower bound is log n, and it goes. I think it goes while communication complexity, but the truth is we don't really understand actually communication complexity of the problem. So that's really interesting question. What's the communication complexity of at a distance? And some version, of course, if you want to exact, then it's hard. I think that's easy. But if you want to, you know, approximation, it's not extreme, and it's related to these embedding questions. And we have actually also like with Dipterka, Chakraborty, and Alazar, we have a randomized embedding which actually has distortion only order k, and I'm going to show it to you because it's very simple. And it actually it goes back to this algorithm by Barna. So if k is you know, if the k is smaller than this number, then we actually are beating Ostrovsky-Rabarny, but otherwise they are better. So I think that the result is better, and it will be very interesting to improve on the result. So let me show you embedding of array distance to Hamming distance, just to give you some idea of what you could do. So my embedding is actually going to take my string x. It's going to be really simple. You take my string x, and I'm just going to basically like repeat every character multiple times. So if I start from x, this is what I may get. And there is going to be some randomness involved. So basically what I'm going to do in some sense, like from distance, I'm going to flip a coin. How many times I'm going to repeat it? So I flip a coin. If it comes head, I repeat. Otherwise, I move to the next thing. So that's the game. Of course, if the randomness would somehow be uncorrelated between x and y, then you will do very badly. Because if you just do it with fresh randomness on x and y, the strings will just be misaligned, and you will get like garbage basically. So the question, how do you align it? And there is a trick. So what we are going to do, so we are basically, the algorithm is here, but what we do is we are basically going to scan x and the output. So I have some index I and j, and I will use some hash functions, h1 up to h3n, And each hash function actually is for a particular output position. So for each output position, I have a hash function, and that hash function will tell me whether I should move in X to the next symbol or not. So what I do is I actually over here I apply the hash function on the output bit I just actually output. This is the J's output bit, so I apply J's output hash function. And if it tells me 0, then I stay where it is, and if it tells me 1, then I actually move to the next bit. So the hash functions, if my alphabet, the input alphabet is 0, 1, then it just outputs me 0, 1. But it would work for any other alphabet over here, and I just like to tell me either to move or stay. Yeah.
I'm not trying to say. So yeah, how do you use a random R?
So the R, you basically like take this R to be these hash functions. So the random, so you get like, you need like 3 or maybe 6 random bits, and they tell you basically, well, they specify these 3 hash functions. So
R is 6 n.
Right. So R
You will append it to the string, right?
No.
Or it's known to everybody.
So I assume it's actually known to everybody. You could actually use Nissan's pseudogram generator to actually just like use basic output of his pseudogram generator as the randomness. Because everything is kind of like small space stuff.
So what's the length of the fx?
So it's actually exactly 3n. Sorry, I didn't say that. So the length of the outputs is exactly 3n.
So again, how do you map them?
Right. So you basically start with I over here and J over here, and at each time step, basically like you output a bit where you are, on which you are looking at. You are going to advance J by 1 position, but before you advance J by 1 position, you basically decide where you are going to advance I to the next position, and you advance it if you advance it basically by 1 if the hash function for the J's output bit of XI, of the bit which you just output, actually tells you to advance.
So a priori, it could be that you don't even write the whole string out.
Right. But that happens with exponentially small probability. Most likely the length of the output is going to be like 2n or something. So like there is extra space which you just fill in by zeros.
So this to make sure that you always have the same walk on the line for every string.
Right.
The same analysis.
It's the same analysis, exactly. So let me show you animation. How does it work? So why does it work? Well, you know, like if you look on AA, we start with 2 strings. So if you output the same bit, then you are using the same hash function or same value, and you are going to perform the same advancement in both strings. So over here, we actually state and then we advance. Then we output next output with, again, we make the same decision. And eventually when we arrive at 2 symbols which differ, we are going to output different value here, and we are applying hash function on different basically like at different points. So it's going to tell us different thing. And you know, in one it tells us to advance, in the other one maybe it tells us not to advance. So it's exactly like the Barnas-Sahas algorithm, where you basically, whenever you run into different symbols, you basically flip a coin. And the analysis is basically exactly the same thing, right? So this is basically just how you basically zip through this. And because of the analysis of Barna, basically what you can show is that the number of differences is going to be again like order k², number of differences you encounter. So somehow magically the strings get aligned, and that is the procedure. Okay, so this was kind of like a detour, like historical like excursus and motivation for what I'm going to show you. So next time I'm actually going to show you something about this sketch of size k times 2 to the square of log n. And before that, let me actually just make a commercial break actually. So we are actually organizing a workshop at DIMAX in May, which is on pretty much embeddings of at a distance, but also other metrics. So in general, like high dimensional metrics. And we are interested in new tools and things. And it's organized by Alex Andone, Barna Saha, Mike Sachs, and me. So feel free to come over. You may want to register; it's for free, so you can just go by also, but that's fine. So let me take a break here if it's okay. And
You're on the boss.
Yeah. So I'm taking a break.
Yeah, very good. How long? 5 or
5 minutes.
Okay.
Let's get started.
I need to get back.
Yeah, I guess so, yeah.
Try to get out of park.
I was gonna leave it like. I don't know.
What?
Oh, no, there's like there's some like.
Oh,
What?
yeah, but the time
That's with the professional.
shatters my schedule.
I also live in workshop.
I decided I did
Yeah.
One band.
It's weird.
And
It's weird.
you-
Yeah, like I'm not gonna try something hard. Oh, you can't buy it. That's some
Is it going somewhere? Is it going somewhere?
Yeah. Like for some, like we found like the
I just
some still.
wasn't really planning to do anything.
Good to know things that don't work too.
Yeah.
Yeah, leave the build in.
I thought about the
for
algebra.
15 minutes, I suppose.
Yeah.
Actually, I didn't even walk.
It's funny that you
That
can do
one.
it for like sensitive.
So one of the was minus.
It is. No, we're just talking about this last week with Russell.
Right, yeah.
Again, on this.
Like solve-
The other idea was essentially.
Not like, I think it's a little.
Yeah, I don't know.
We haven't worked out the parameters, but we can talk about it.
Yes.
It's clearly very related.
Yeah.
Yeah, but I hadn't known about it until like 5 days ago when Russell.
Oh, yeah, but I don't know. Once you get older, the things you know you forget, and that's, it's all perfectly aligned. You want to know your future.
Yeah, that's right. Russell has forgotten everything that I even know.
Well, you know, the physicists come up with it, but not in the, if I had, I mean, there are much.
Can do morning. Like if you, I'll be here in the morning.
The
Play by ear, depending on
I think it should be here in the morning.
There's a very
like
comfortable
9:30ish.
even thing that something like this might,
Unless there's
I mean,
some,
hashing is so,
it's worse.
you know,
Something.
designed
Mhm.
so that the outputs have nothing to do with it.
Right, well, it seems like at some boundaries, like you should have major issues.
The hours, no.
I don't know.
Yeah, we had that.
The primary feature of
No, there's something else.
LCC.
Yeah, to the K to the 1/4. Yeah.
Right.
no, anything.
Should not correlate.
Yeah,
Yeah.
just different.
I mean, I shouldn't call it.
In one bit.
We didn't really do it.
Thought would work.
I think so. This is the log cube that I was pointing out, that you could in principle get to the K to the 1/3.
Yes, something that's.
So he gets for designs, he hasn't gotten it for all things yet. But I think that also can be made to work.
Very cool. I don't remember who was the best locality.
And that's what we've been saying. What to do about the last log.
Yes, Alex.
Yeah, maybe I will.
This paper should really be written on or nothing, right? Like I don't know.
That's not actually. I
Who
can't.
is the best locality strategy?
I should know, but I don't.
Peter
I don't know.
bummed that I didn't let him write log cube down.
Oh, good. So amazing idea.
Yes, yeah, I mean, he understandably thinks, I suppose, that he could have gotten other papers.
Yeah, well. Also, it's important what metric you are in.
It's not as exciting, the same as.
For the other question.
He does, so we have like a slightly.
Yeah, we were thinking.
After we had the first paper. There's this so-called edge deletion.
Okay.
That's really the. He doesn't put it this way. I can tell you, it's very nice. Actually.
I know it's better.
Yes, that's true.
I don't see it. The thing is, the arguments you get rid of them, that's the exactly.
Yeah.
It's to expand your fast.
Connectivity.
You are solving a problem. We just solved it.
You're being sarcastic.
Ever.
Yes.
Okay. I wonder this, the topic. Okay.
Okay, so now actually it comes like the new result stuff. So I'm actually going to tell you about locally consistent decomposition of strings, and that's going to be our tool to build better sketches actually for any distance. So what do we want actually? So we have seen that the problem of actually computing at a distance for x and y is aligning properly the pieces of x and y. And imagine we would have like some magic tool which would break the string x into pieces, into blocks, and string y also into some blocks, so that the matching blocks would basically be nicely aligned, and then there might be some pairs of blocks where there are these edit operations, and then again like there are these nicely aligned. So so such a tool would be actually useful to build a sketch. So it would kind of isolate. So the goal would be to isolate basically these differences into these blocks. So of course this is a trivial. What's the trivial solution? Just take the whole x as one block and the whole y as the other block, and we are done. So I had to put some constraint on this block, and I want to actually make them small. So I would like these blocks which contain the edit operations to be small, because if I succeed, then I'm in good shape. Basically, I could basically throw away all the parts which are the same. I can get rid of, and I may get a good.
Wait, but you want to do this independently,
Right.
like for every string, without knowing ahead of time what you're going to compare, right? So
Right. Without actually knowing ahead of time, actually even which thing you are going to compare it to. So that's right. So that's the challenge actually. Right, indeed. And but we have seen that sometimes it's actually possible to do these kind of things. So let's try. So we will try to do that. Now, one thing is, what does it mean that the block is small? And it depends how we measure. And for us, the measure will be actually the size of basically like the compression size. So we will be looking at actually grammar size. So you can actually describe each block by a grammar, and I will remind you what that is. And we want actually that grammar description to be small. So it's not that the pieces are small in length; they actually have like small description. So here is how our string decomposition will actually proceed. So we will chop up x into blocks, into s blocks. Each block will be described by a small grammar, size roughly order k. And if you get x and y independent, like two. Oh, okay. So maybe what's the grammar? So I hope like most of you have seen sometimes like a context-free grammar or like a description of.
I think we went out of the basic computability course a decade ago.
Right.
How many people have seen or have not seen?
How many?
I never got it.
You have never seen it. Yeah. Well, so Abe, I wish you were right.
No, these are maybe they are not.
I think it's just because it's Zipser's book.
I mean,
Yeah, we didn't follow it.
no, if it's Zipser's book, whether it's taught or it's deliberately, it's a statement skipped in. I don't know. What do you do in CMU?
We killed even automata, so I have no leg to stand on.
Oh, you killed automata. Great.
I do one class on DFAs, and that's it.
Oh, wow.
And
That's
I
great.
think this is common. No, in Berkeley, how much did you learn actually in a class about?
Yeah, there is a computability class.
Yeah, but about context-free grammar.
Yes.
You are not skipped. Okay, so maybe I'm wrong.
Yeah, I think.
I heard from several people, I don't remember which university, that they skip when they teach computer, even from CIPSA, they skip this.
I agree, they should actually.
So only you can use that.
Yeah. But a grammar is actually very simple, very simple concept. So you have some these are basically rewriting rules. So you start from some starting symbol S, you rewrite it as AB. Then you like each symbol you get, you can rewrite further by the rules. And in our case, actually, the final you arrive to these lowercase letters, and that's your final symbols.
Yeah,
So
the big letters are like variables.
exactly, the big letters are variables, and you write them using some rule in your grammar. And the grammar doesn't have to be like just produce single string; it may actually produce the whole string. That's context-free languages. But in our case, actually, we will have a grammar which describes exactly one string. So it's actually there is going to be just one choice for the correct basically expansion. And that's what we actually measure. So by the size, I just mean the number of rules. So that's just the number of rules. So the number of rules is going to be roughly K.
So you can do this efficiently,
To calculate the grammar?
like to calculate the minimal grammar that is required.
Oh, minimal
I don't know
grammar.
what the blocks are.
Yeah.
No, like, but given a
Yeah,
string,
given a
can
string,
you say what the minimal
I
size
think
grammar
that-
is?
Oh, that's exactly what people in automata theory actually learn. So
In automata, final automata, you can. I don't think that.
I don't think you can actually do that. I think it's a hard problem, but I'm not sure how hard it is. Well, it's at the most an exponential time because you can actually
Yeah,
try all
but
of
no,
them.
efficiency manifold, I think.
Here you say like you want to cut it to blocks where everyone has a small grammar. I mean, how would you know?
Oh, well, we will just construct them. So we will construct the grammars which are not too big. And I guess maybe, yeah, right. So there are various ways how you can actually, so this is a measure of compression actually. There are various ways how to measure compression. Kolmogorov complexity would be like the strongest. And so the grammar side basically is the Lempo-Ziff thing, actually. It's the Lempo-Ziff compression that actually gives you grammar of this type, pretty much exactly. Model some technicalities.
Well, it's even simpler. It is in this context setting, but it's even simpler. It's a very.
Right, but it gives you a grammar of this type, and there are some restrictions how you actually come up with the grammar. Right. So each block has this small grammar, and then if you take two pairs of strings, then the grammars kind of like nicely align in pairs. So we are kind of like back to Hamming distance in some sense. And there are some grammars which are different. Some pairs are not identical, and that's exactly the blocks where are the edit operations.
So the number of blocks will be fixed.
So the number of blocks will be a random actually. The number of blocks.
So it can be two different.
Oh, what do you mean?
For X and Y.
Oh, no. For X and Y, you hope that it will be the same number of grammars and they nicely align left to right. So that's really the goal. So the goal is the blocks. This should be like kind of like if I would go back to this picture, the grammars should actually nicely align, and this should capture. This could capture. So in particle, if you calculate at a distance of X and Y, you can just calculate the edit distance of the pairs of the grammars, like whatever they expand to. And that's the edit distance. So pairs which are identical, they contribute to zero. So you basically are calculating, you can separate the edit distance computation for the independent blocks, and that's what you want to do. So that's our goal actually. And as we said, we want to do it independently on X and Y, and somehow magically we want to get this. As I said, it's going to be randomized, so there is some probability of failure, which is actually non-trivial, which means you can like make the probability of failure something like 1/polylog n, but not much bigger. So there's no easy way how to do that, but you can repeat it a few times, and then at least one of them will work. So you can kind of like do a good job from this. So let's try how to think how we would go to break the strings actually. And let's take as a warm-up actually random strings, because that actually motivates what's going to happen. So I'm going to pick X at random, complete at random, and I'm going to choose Y so that the edit distance between X and Y is at most k. So Y is kind of fixed, but X is completely random. And so how would we break it actually? Well, if you think about that, well, the natural thing is actually to look on some small windows, because if you look on window size log n, it pretty much determines the substring, because it's completely random. So if you somehow look on a window here and it's of size log n, so this is the window size log n, and you look here, then you are unlikely to see the same pattern anywhere else. Or if it's like 2 log n, then you are pretty much guaranteed you won't see it anywhere else. So let's just actually kind of scan and see what we are getting. And we are going to actually break the string based on what we see in that window. So how do we do that? Well, we pick some random hash function, which maps log n bits, so basically the content of the window, into some range from 0 up to 8k log n. And if the hash function tells us 0 on a particular window, then we are going to chop it off. So that's our procedure. So what really actually matters is that basically this difference between 0 and anyone else. So it doesn't have to be this range, but the probabilities should kind of correspond to us if you were doing this. So how this thing is going to be chopped off? So in this particular example, let's say I actually pick a hash function which tells me chop off whenever you see 0, 1, 1. Then you should chop it off. So I actually marked for you already these places, but let's just play the animation. So over here you have actually one block starting block, and over here you have another. And if I run the same procedure on the bottom string, well, what happens? Well, I break it here and there, and voila, that's what I wanted actually. So I'm in good shape.
Do you want to get something like polynomial in k blocks?
Polynomial in k blocks. No, the number of blocks may be n over k. You would expect.
N over polynomial in k. So it's the length of the blocks.
Right, the length of the blocks is going to be like roughly k. So in particular, let's analyze this. So let's see. So you see that this time we were lucky, and actually, we broke it in places where we could break it, and we are happy. So let's see why did we succeed actually. So the reason why we succeed is because what could go wrong? The only thing that could go wrong is that we would break it in one of these windows, which kind of are around the edit operation. So if you break it somewhere over here, and there is like 2 log n windows up here where it's dangerous to break it, and there is like 2 log n windows down here where it's dangerous to break it, and they contain some small strings. So there's like for each edit operation, basically there is like 4 log n windows where you don't want to break it, and if you break it anywhere else, you are happy. And the choice of this 8k log n is exactly such that basically you are unlikely to hit it, or probability that you will hit one of these bad windows is like 1/2. So I have like 4k log n places where I don't want to break it. These are windows, but for each window that I break it, this probability is like 8k over log n. So the probability that I will hit actually one of these edit operations, or like in the neighborhood of it, is like 1/2. And so that's why I actually have chosen this 8k log n in this argument. And what's going to be the length of the blocks? Well, in expectation, if the string x is random, you expect the size of each block to be roughly 8k log n, because that's how often you basically decide to break it. So the blocks will have exactly the size I promised, and there's a good chance you don't mess up the strings. So that's for random strings. How about non-random? So let me take the most non-random string I can think of. So this is all zeros, and let's see what this method actually does. So so what happened? Well, nothing has happened because it's all zeros. I see all the time all the same thing. So what's the problem? So the problem is kind of low entropy. If the string would be kind of random, it would look like the picture before, I would be fine. So how do we increase entropy? By compression. So I want to actually compress the string so I can concentrate the entropy, which is in the string, and the procedure which we had before actually would work. So let me actually take some other example. So this is like again like low entropy string. So there is not much stuff. There is a big block of zeros. There is like a big block of zeros at the end, and there is this kind of maybe looks the same. So I want to actually compress it to kind of like concentrate the entropy. I don't want to actually compress it too much. So maybe I'm going to be modest. So I'm just going to do a little bit of compression, and then I see whether I actually when I'm in good shape. And so how do I compress? Well, I'm actually going to compress the long stretches of the same symbol. I just will have some special character which tells me, well, take this character and just repeat it so many times. So I started with my original alphabet sigma, which was the input strings, but now I will be actually working over some slightly larger alphabet gamma. So I have some room, and the size of gamma is still polynomial. So maybe like n to the 7. I'm not sure what the numbers are, but that's roughly what the size of this working alphabet is. So it can, in particular, accommodate all these repetition symbols. And then I want to, so basically that handles these long stretches of zeros. Now I need to handle also the parts which are like singletons. So the singletons, I need to break into pieces and compress those pieces. How am I going to do it? Well, I'm basically going to I want to like group them together and then like compress each part. And I'm going to basically pair it into, well, I'm going to couple it into pairs or triples. And using some special procedure, which was designed in the 80s by Kohl and Mishkin, I will tell you what the procedure is. And then in each pair, basically, I'm going to compress the first two symbols into another like compression symbol. So this compression symbol says that you should expand it into 1, 2. So it's like this variable from the grammar. This guy should go into 2, 0. This guy should go into 1, 2. And you just write down in triples. You just write down this extra symbol. You just write it down, and that's it. So if you do the calculations and you look on the string, then the string shrinks by a factor of at least like 2/3. Well, depends how you calculate. Well, basically, like you will end up with a string of like 2/3 roughly, in the worst case. So that's one level of compression. One has to take care actually of how to break this sequence. And let me show you why is that actually important. Because imagine that x and y would just consist of singletons. So every symbol is just like sitting next to a symbol which is completely different. Well, it doesn't have to be as much as this, but even like A, B, A, B, A, B, A, B versus B, A, B, A, B, A, B, it would be a problem. Because if you just break it naively left to right, what's going to happen is that you will have this pair of symbols will have different compression symbol than this one, etc. So you will end up with strings which look completely different. So after the compression, basically, when we basically compress these symbols, my new string is going to consist of this compressed string, and on that one I'm going to basically break it into pieces. I'm going to apply this splitting procedure again, and then compression is there. So in this case, actually, I would basically like amplify this like single edit operation. I just amplify it all over the string. So I don't want to do that, and so I need some scheme which partitions these two strings in some manner that like the parts which look the same actually are divided in the same way. And I guess one could use actually randomness to do that, but there is a deterministic like beautiful result by Kohl and Mishkin. So this is kind of what I want, and there is a beautiful result by Kohl and Mishkin, which actually can do this kind of stuff. So this is their algorithm. So I will start with a string which consists of singletons, They don't have to be all distinct, but just like neighboring guys have to be different. And I want to actually come up with some, so that's what I call proper coloring of 1 up to n. So 1 up to n that are positions, and I get 1 up to little gamma, that's my alphabet symbols. And I want to actually proper color it by just 3 numbers, 1 to 3. So from these symbols, I want to derive some new symbols, 1, 2, 3, 1, 3, 2, etc. And the goal is I will be breaking it, like whenever I see 1, I will break it. What I want from this coloring is that if that like a value over here depends only on some small neighborhood around here in the string. So in particular, I want that that this coloring of in the ith position depends only on some window in the original position in the original string of symbols I minus r up to I plus r, where r is, it turns out that you can actually choose r to be like log star gamma. So log star gamma is like how many times you have to iterate log to get to 1. So that's the log star function, which grows like super slow. And you can actually do this. So there's a procedure where each color, resulting color, actually depends only on this small window. The neighbors have different colors, and you can make it so that like out of every 3 symbols consecutive, you have at least 1. So then if I break it at places where you got 1, you actually you will break it like into pairs or triples. Because it's proper coloring, you cannot have like 2 1s next to each other. So,
Proper coloring of the graph is a path.
yeah, exactly.
It's not clear from the material.
Yeah, okay, yeah. So
Coloring
it's
is the coloring of a path.
right. So and by path we mean actually this graph which is behind that, which just says who is neighbors of who in this string.
The original motivation is the distributed computation, and it's sort of was mind-blowing, I think, to everybody who saw this originally. There are n processors sitting on a line, and they each, have a number between 1 and n, but you don't know it. So from some name space, they are individual, and they want to properly color their position in the, so they each choose a color so that they should be different than their neighbor. Maybe it's a cycle, maybe it's an odd cycle, so you cannot do 2. I mean, even if you are, from the outside, but they want to do it distributively. And you can do it with 3 colors, even if you know only your neighbor's colors up to a short distance from you. Which is unbelievable. I mean, you have to know everybody. You have to know the parity of n or whatever, how many you don't need anything. If you just know, the colors of people log star away from you, they can consistently and deterministically choose the color from themselves. And everywhere in this arbitrarily long cycle, everybody will be different than their neighbor. So it's an exercise to find.
Yeah, it's a tricky exercise.
It's
It's beautiful. I mean, the whole algorithm is like, 50 years actually.
Yeah.
It's amazing that you can actually do that, and right. So that's what we are using. Okay, so that's the color reduction, and so you break it at these ones. So that's our compression. So our compression is basically going to, as I said, you compress the repeated symbols, then you use this Kohl-Wishkin procedure to divide into pairs or triples. You compress those guys, and you get a new string on which you are going to apply again the same algorithm, the same procedure. So the whole procedure, this whole decomposition procedure, is you always like try to split with the same parameter k, and then if it you split whatever is kind of like is split, and then the blocks which you are left with, you compress them and try again like to compress them, to split them, and you basically repeat this. And at each stage, like things either like get smaller, so because you are compressing, or they actually you are breaking them apart. And what happens is that basically, like as you are, this compression actually corresponds to to basically building the grammar. So this is going to be my rule. I'm basically in my grammar, there is going to be a rule that you should have C12 is actually going to be decompressed into 1, 2. So that's basically how the grammar actually arises. So as you are compressing down, if you go backwards, that's your grammar.
But C12 is not really a compression, right? I mean, it's the same, you know.
Okay.
In terms of information, it's the same information. It's not really compression.
Right.
You gain only from this long constant string, right?
I'm actually cheating you. I'm hiding some stuff. So actually for this compression, you are using like a random hash function to actually get this. So it's not actually the C12. I'm cheating you. It's not like single. It doesn't have like a unique preimage. So what you actually use, for this compression, you use some compression function, which is a random function on your alphabet, and it goes from pairs to pairs to singleton, and you use that as your guide for the compression. So I'm cheating a little bit because otherwise the information will get lost. So it's not the decompression is not unique, and you have to actually put in the rules which you are really using. But with high probability, there will be no collision because the compression function, just the range of gamma is so big that whatever you are going to see is always going to be different.
So the alphabet itself will be logarithmic or something.
No, it's polynomial actually. It's polynomial size.
No, okay, polynomial size. I mean, you look at blocks of log and characters, really. Yeah, okay. The alphabet is the polynomial size.
Right.
And that doesn't fluctuate the complexity.
Say that again? No, it does not. No, it doesn't.
Oh, because the string.
It's going to be sparse. Yeah, right. It's short or sparse for them. So yeah. So actually, what we do is I kind of like gave you this example at the initially the motivation where we were looking on window of actually log n symbols, and we were like moving that window. But eventually, what we do is we actually looking only on window of 2 symbols, and because the alphabet is big, eventually these 2 symbols may actually have enough entropy, so you actually make a reasonable decision. So it's not actually that you're looking on window of length of long window, but we are using actually windows of size 2, and we are compressing 2 symbols into 1, and this is actually not coincidence. These 2 are kind of like matching each other, and the point is that what happens is that whenever you are basically why do you do compression? Because like if your decision is based on pairs, the reason to basically make a compression is because your string doesn't contain many different pairs. So if you contain a lot of different pairs, consecutive pairs, then you are going to break it. If you don't contain many consecutive different pairs, then you are not going to break it, but then the compression kicks. So, but the compression, if you have not many pairs, then you will just have few rules to actually put into your grammar. Or you will actually observe only very few distinct pairs in your string. And that means that you are observing only like at most k different pairs. If you are not actually, if the splitting didn't kick in, then you have like few pairs. So you have few additional rules into your grammar. If on the other hand, if you have a lot of different pairs like next to each other, then the splitting is going to kick in and it's going to break the string. So that's why basically like at each level, whenever you compress, the number of rules for a given block, actually the number of rules you will need is like roughly order k. So at each level you introduce like k new rules for each block, like in different blocks differently. So this gamma square and gamma square, it's not coincidence, it's on purpose.
So this is similar to language decomposition.
Yeah, it is. Except maybe on Lampos if you have this constraint that it has its previous window and of some size and stuff. So this is the string decomposition procedure. And somehow what happens as we are compressing the string, well, the edit operations are contained somehow like hidden beyond some symbols, and the number of symbols behind which they are hidden is basically bounded by, well, whatever your neighborhood size is from the Kohlwishkin, but it may like slightly grow because of the Kohlwishkin, but it's basically constrained. So like at each step, basically there are like order k places which you want to avoid, and otherwise you can happily break it at any place which avoids this edit operation, which are hiding beyond some symbols. So that's the string decomposition. If you don't catch any all the details, you can read our paper. It's actually fairly simple. It's really simple. So this decomposes string X into these grammars, and each grammar is going to be of size order k. So as an application, you immediately get basically the sketch of size order k squared, because you just run this grammar decomposition on both strings independently, independently on X, independently on Y, and then you get the grammars. But these grammars have like k rules, roughly k rules. Each grammar can be described by log n bits, so you can just describe it by string of size order k. I'm ignoring log factors. And so each block, basically each of these blocks, you can pet it, so it's exactly say k. So you have these blocks which are like exactly k size, and you just line them up, and that's your sketch. Sorry, that's not your sketch. That's
a little bit too long.
Right, it will be too long, but now we apply actually sketch for the normal Hamming distance. And if the two strings are identical, so they have the same grammar, which actually the procedure kind of guarantees, then you don't need to recover it. So what you only want to recover is these different grammars. So each different grammar is like k bits in length. There can be k of them. So if you have a sketch for Hamming distance up to size roughly k, capital K, where capital K is k squared, then you will be able to recover these grammars which are different.
Yeah, but you need the sketches to actually do error correction or detection, right? You have
Right.
Not what you promised.
Right, I'm still cheating you. So the problem is that if the two grammars actually, they may be different, but you would just recover the differences actually. So you need some kind of error correction. And like there is like easy way out of this. So is that basically you just, for each string, basically which is hiding behind the grammar, you just compute some fingerprint, and you somehow encode it. Just multiply it by this. If you think of it as a binary vector, well, think of this binary vector over some bigger field, so you just multiply it by the value of fingerprint, and that will kind of like all the bits will show up. So there is some trick behind it, but I will actually get to it in the second application. Right, so there is some technical thing you have to do, but that's not hard. So this sketch you may use is actually either the one which you have seen, which would just use like some standard error correcting codes, or you can use some more fancy stuff like the one by Clifford, Kotsumaka, and Pora. So they actually the advantage of those sketches is that they actually have fast decoding, fast in the number of operations, in the number of basically edit or Hamming operations, and they can also tell you what the differences are, and they can also actually modify the sketch. So you can actually append symbol or remove symbol, and kind of there is like an update operation for those sketches, so, which is useful for some applications. But the vanilla sketch would work. Vanilla Hamming distance sketch for k-squared would work. So that is the whole sketch actually. So how do you go from here if you want to actually make it shorter? And so let's move on to this next thing. So how do we make it shorter of this size k times 2 to the square of log n. So that's the work with Mike. And so what did we do before? So before we took X and we broke it into these grammars, G1 up to GS, and there's a superscript 1 because it's like one level. So what was the problem? Well, the problem is that we are spending too many bits maybe on grammars which are not that different. So sorry, which contain just few edit operations. So we are basically like we have these k grammars, each of them may contain up to k errors, so we have to recover the whole grammars, and that's like k squared bits.
Just curious, like, so all these like previous polynomial 2K sketches or using this tree of grammars, like using this.
Oh, that's a good question. Thank you for this question. So all these parallel sketches actually were based on this embedding of edit distance into Hamming. This is the Barnas-Sahas type embedding. So they were actually using this, and it was actually fairly complicated. So it was like a very sophisticated method. So you had to run it multiple times. Then you look on kind of like what are the common edges between the matchings which you obtain, and that was sketched somehow. It was really complicated. So this decomposition actually gives you like much simpler way to achieve the same.
So you mean this the first the breakthrough is not using this grammar, or like
Say it again.
so sorry, what do you mean? Like
The first breakthrough actually wasn't using this.
wasn't using this.
No, it was using this. So this is actually new. This is from last year. So that paper was using this technique of mine actually with this Diptarka and Alazar. So this random walking.
I see. Thanks.
And so maybe we are hoping for more application of this technique. Yeah. So let me just comment. So originally kind of like we are trying to get actually this decomposition. That was kind of the original goal, at least what I have in mind. And we didn't achieve that. What we got was the thing before. And I think now kind of we nailed it. So for the tree of grammar, so the problem is that each grammar can be of size k. So it's natural if some blocks actually contain fewer than k edit operations, you would like to subdivide them. So let's just try to do that. So we just subdivide them all the way down. So what I mean by that is that you basically run the same decomposition procedure on the string which is over here, but with different parameter for the grammar size. So this k basically controls how big the grammar is, and so we just do this whole tree all the way to like tiny strings.
And you don't have the promise now, right?
Right, you don't have the promise. Actually, the promise is out of the window, actually, and we will have to deal with it. So that's the challenge, actually. So in principle, here is what we would like to do. So we would like to recover in this tree. We would like to recover some of the grammars, and which grammars we would like to recover? Well, we would like to recover the grammars which roughly have size as the number of edit operations between the two strings which they cover. So that would be ideal. So maybe we would pick a string grammar here, and grammar here, and that would cover all the errors. So that's kind of what we want to do. Of course, if you sketch it, well, the problem is that like there is a lot of things which get just like below this knees. The stuff may get broken completely wrong way. And if you would just sketch everything by one sketch, then it will not work. So we will have to be more sophisticated. And what we will do is actually, well, one thing which we will do is that we will actually sketch each level separately. So at least we have like the grammars of the same size. We are trying to sketch, and since there is only log n levels, that's fine. So each basic level will be sketched independently, and we will want to actually recover somehow the relevance. And we will have to see what does it mean that the grammar is relevant, because so far actually there is like a lot of errors all over the place. So let me just make some. So one thing is that actually encoding matters. So how we encode the grammars. So let me actually now tell you how we are going to encode it. So in this particular context, it's actually useful to encode it as a sparse vector of like gamma cubed. So the alphabet is gamma cubed, and all the rules are basically from this set gamma cubed. So I'm just going to encode the grammar as a binary vector of like gamma cubed, and it's going to be sparse vector. It's going to have k1s at most, or roughly k1s. And what's nice about all these Hamming sketches is that they don't really care. Their dependence on the length is like negligible. So if you kind of like take super long strings, once you sketch it, the sketch size depends only on how many ones you want to recover. It doesn't really matter on the size of the string. So this gamma cubed, even if it's like n to the 21, you don't really care. It doesn't like translate that much into the size of the sketch, because the strings are sparse. And in this sparse representation, what happens is, and that's important property, that if you have two strings x and y, and you build a grammar for them, then the Hamming distance of the two grammars is actually bounded by the original edit distance. And this is kind of like you should kind of see it from the picture how we build the grammars. You know, the edit operations kind of affect symbol roughly always at each level. So the number of rules which are going to be affected is like logarithmic in the edit operation roughly. So if you have this representation, then each edit operation translates in the grammar into small Hamming distance. Basically, like there is kind of like bijection between the number of edit operations and Hamming. Unfortunately, this doesn't go the other way. So if the Hamming, you know, we may have edit distance which is, I should be saying that. I should be saying that. Okay, sorry. This should be actually edit distance. Oops. So the point is that the Hamming distance is bounded roughly by the edit distance. That's what I wanted to say. But it doesn't actually go the other way. So you could have actually added two strings which are very different, but they have almost identical grammar. The grammar differs just by one rule. So that's actually a problem for us, and you will see where it comes in. And over here we are going to use watermarking of the grammars, which solves this problem which Ade raised. So for a given grammar, we are going to compute some watermark, which is kind of like fingerprint of the string behind it. And we just multiply the 0, 1 vector by that watermark over some bigger field. And that kind of means that the ones will be kind of visible. If you take two grammars which have different watermark, then you will actually see the ones where they appear. And that's good enough for us to recover. So that brings me to fingerprint. So what is the fingerprint? So fingerprint is basically this embedding into overdrive. So what that means is that I'm actually mapping strings into not like log n dimensions or something, but I'm just mapping it to a single integer. And so there is a standard fingerprints by Karp and Rabin. So if you have two strings x and y, then if the strings are identical, then you get like identical fingerprints. If the strings are different, you get different fingerprints. It's a randomized scheme, so there is some probability of failure, but that's actually negligible. But there is something more interesting, and that's the Ostrovsky-Rabani fingerprint, which is you can derive from basically the work of Ostrovsky and Rabani, and that's you take strings and you map them into integer, and it has the following property. So it's parameterized by k, so you have to choose what k is. And if the edit distance of x and y is most k, then the fingerprints will be the same with high probability. And if the edit distance is actually bigger than k by this factor, which comes from this Ostrovsky Rabani distortion, then the fingerprints will be different. So this allows you to do that if actually you can actually selectively basically watermarks grammars which you want to recover. So the grammars you want to recover are the ones where there is the edit distance is large. So you want to actually recover them, so you are going to watermark them. And
what formally do you mean by watermark? How should we understand what watermark?
By watermark, I mean I multiply each one by this fingerprint. So instead, I basically replace each one by the output of this function, by the same output. So instead of vector 0, 1, I'm going to have a vector 0, 7 for one string and maybe 0, 15 for the other string.
Why you call it a watermark?
Okay.
Watermark is supposed to protect ownership or something. But I don't know.
Yeah, well,
You're simply multiplying by a constant, by a
Right.
random constant.
I'm multiple. Well, the constant has meaning, right?
Yeah.
Sorry, could I ask how that claim about like if the edit distance is small, then the fingerprints are equal. If it's large, then like, how does that follow from the L1 embedding theorem?
Oh well, it's not completely like it's not like immediate, but if you think about that, actually, maybe you have to massage a little bit the Ostrovsky-Rabani embedding to get it, but it actually follows from.
I guess I was asking, does it follow from the L1 embedding theorem or does it follow from the proof?
I think it actually that's a question we didn't quite like kind of settle on. So it's true, but I think it's probably like generally actually true if you have any L1 embedding into L1, as long as there is some reasonable properties and it's reasonable. Actually, you can get this. It may not be true in general, but for some nice embeddings, it is true. So here is what we can do now. So basically, like we can, if we watermark or multiply these grammars by the constant, like the appropriate fingerprint, then that makes sure that this grammar will be visible from the Hamming sketch of this guy. So these things will be visible. For things which we don't want to see them, oops, sorry. They won't be visible. So for example, we want to also see this guy because it has like relatively high edit distance compared to where it kind of sits. But if you think about that, so these guys we want to recover completely. So we want to recover full grammar. But if you look on grammar over here, because over here there is some edit distance, which means that these grammars actually are different. So this is actually a different grammar in X and different grammar in Y. And we don't want to recover it. It's a problem for us, but turns out that this is not a big problem because the number of differences we can actually get in this grammar is at most the number of edit operations in that block, which is bounded by this. So somehow the lower level kind of edit operations actually contribute also over here, but the total number of these sporadic differences between grammars is actually bounded by K, or rough order K.
So it's not really changing by factors too. You really can only approximate the number of edits in a block up to this factor, I don't know, to the square root.
Right. So our goal is really to actually reconstruct the grammars. Or maybe I should have said that. So our goal is not to actually estimate the differences between the grammars. Our goal is actually to really like get hands on the grammars and then actually compare the grammars.
Right, but the way you want to do it is not to play the K squared, is to really estimate how many edit operations are in a block, right?
That's kind of we need to do, right? Kind of like the scheme.
I mean, you will not save, or you will not be able to.
Right.
I mean, you said that initially the problem is that the only K edit the distance K, but it's in K blocks, and you don't know if one block contains K of them, or K of them contain only one edit. Right. So for this you want to approximate somehow the number of edits in a block. And this is what the approximation you just mentioned up to this factor, which comes from Hamming embedding allows it to do. It is true.
That is true. Yeah, right. That's true. But it's kind of like the whole thing has to be kind of transparent because you don't know what the other thing is. So you have no idea which grammars are relevant. What is the edit, whatever. So
you contain this potential.
Right.
Going all the way to the end, you don't know really which one.
Right. What's happening? Like when you are building that, you have no idea whether you will need this grammar or that grammar. It's just kind of like it has to work everywhere, kind of like seamlessly in transparent way. Say catalytically. So that's one issue. So basically, so we can make sure that these grammars which we want to recover will be recovered in full because they have this distinct fingerprint. The grammars which look a little bit different because they have like few differences, we may recover some rules from those grammars, but we won't be able to actually reconstruct the whole thing which is sitting there because it may just be like one rule is different there, and it doesn't actually tell us anything about the rest of the string. And in order to actually calculate the edit distance, you need the whole blocks. So you have to recover the whole grammar. Okay, so that is actually one issue, but it's not actually the only issue. So let me go back to this problem, which is actually kind of serious problem here. And the serious problem comes from the fact that as we are breaking down the grammars, actually farther and farther, if this grammar already, like there was a lot of edit operations behind this grammar. Like you can expect that in the next block, it will be broken completely like in wrong way. Moreover, actually, this tree is not bounded. The degree is bounded by n, because you may have like up to n different subblocks. And, like one mistake can actually like make that there is going to be like n distinct grammars between x and y. So the number of actually errors here, the number of distinct grammars here on the next level may just blow up completely. You have no control over the number of distinct grammars over here between x and y on the next level, because like you can make a mistake in breaking the blocks, and that actually shifts the grammars by one. There may be extra grammar for x sitting at the beginning compared to y, and the rest is the same, but they will be shifted, so everything will be different. So that's a problem, because if you just apply ordinary sketch for Hamming distance on this thing, you will actually likely this will like overwhelm complete the sketch, and you won't see anything. So we need to actually work with that. And what we do is we design a tool which is kind of like the main technical tool of our thing, and that's what we call the hierarchical mismatch recovery scheme. And it's built in particular for this particular application to recover the errors. So what is this hierarchical mismatch recovery scheme? So imagine that I give you two strings, x and y, and the strings are divided into blocks, and I'm actually measuring a Hamming distance between two blocks, and I want to actually recover the errors between the various blocks. But some blocks may contain a lot of errors, a lot of mismatches, and some blocks may actually contain just few mismatches. And what we care for is actually the blocks which contain few mismatches. So that's what we want to focus, and that's what we want to recover. So let me, but that's not actually, it's slightly more complicated. That's why it's hierarchical. So here's what I'm going to do. So I'm actually going to define a load. So that's the number L000, etc. for this, and that's just the number of differences between in this block of x and y. And then I'm going to actually inductively define load at higher levels. But if the load is too big, beyond some capacity I can afford, I'm going to chop it up. So here's so I have some, for each level I have some capacity, kappa 1, kappa 2, kappa d. So this is 3 of depth d. And higher up, I'm basically going to compute the load of that node as the sum of the loads of my children, but I kept it at the capacity of that node. So each node has a capacity, and it's the same for the nodes on that level. So I basically like threshold how many errors kind of are loading from below up there. And what I want is that here's what I want to recover. So I want to recover blocks which don't have too many errors, and also which don't actually pass through nodes which are like overloaded. So if I have a node which has a big load, then I don't care for it. What's the rationale? Well, if there is a node which actually carries a lot of load, then most likely he is passing through some grammar which we are going to recover anyway, so we don't have to like care for it. So the grammar for that node should be recovered, but we don't have to recover the stuff from below. And so that's what the hierarchical mismatch recovery actually stands for. So the goal, so you want actually to sketch x and y in such a way that you can actually recover these blocks which don't contain too many errors, and the path to the root along that nodes is not overloaded. So 1 over d overloaded actually technically means that your load is below your capacity by at least 1 over d factor. So your load is at most like d fraction of your capacity. So you can imagine that this kind of gadget can be actually constructed, and that's exactly the gadget we need. So what the gadget basically does, it kind of suppresses the places in the tree where there is a lot of errors, and it lets you recover the pieces which actually contain just few errors. So we have a kind of like nice, easy randomized solution for that based on work which others did in past, but it's not actually hard to do. So if we apply it, so what we do is we actually apply this tree, this hierarchical mismatch recovery scheme on each level independently, but then the capacities are basically set to the grammar size, more or less. And what it does is that it kind of like suppresses these like huge number of errors here, but it lets you to recover the portion which contains few errors. And that's kind of like what you get. So you get a sketch of size this k times to the square of log n, and not only that we actually can recover the edge distance, we can actually recover the optimal sequence of operations, which turns out to be actually a necessity because we have to repeat this multiple times and we have to actually kind of retain the edit operations, which kind of like are very often prevails. But that's kind of like a small technique. So I guess I have like one more application, but perhaps this is a good stopping point. So let me just stop here. You can go for lunch.
All right. Thanks. So questions? Can you summarize this result? I mean, this something mysterious about going down from k to k squared, then to something which is k to much less than k squared, almost linear in k.
Mm-hmm.
Okay, you gave some technical detail, but is there like beating the birthday paradox in some sense?
Right.
Is there what can we learn from it that's beyond edit distance? This is a problem that comes up all the time, right?
Right.
Asking.
Right. So I don't have a good answer. So I know what you're asking. I don't have a good answer. Indeed, actually, up until we did it, we were not sure whether it's possible.
Okay, here's a similar question. Could you, with these tools, could you directly have a humming sketch scheme? Do you actually need it, or?
You mean, do you need the Ostrovsky?
I know you use it, but
yeah. Okay,
mismatch.
That's a very good question, and I think that's worth actually like thinking about. I don't have at this moment I don't have an answer to it, but I agree. In particular, I think if you would be able to push it like to really linear, then it seems to me that should be basically a Hamming scheme, just like out of the box. I kind of I see what you are saying.
Yeah, I mean, given the result or given your result, it seems like once we get maybe polynomial there or something.
Right, just by measuring basically these grammar differences. I tend to agree. Yeah.
More questions. I have just one comment about the Korvishkin. I didn't want to say too much, but I think really everybody should know this. I'll say two things. So the result is more, well, the original Korvishkin is, as I stated, you are coloring the cycle with 3 colors, completely distributively, deterministically, when each processor just knows the log star neighborhood. This is true. First of all, this is type, the result of multilinear. You cannot beat it. Log star is what you need. And the second is that it works for any graph. If you have a graph with degree is bounded by D, processor on every vertex, they can color it in D+1 colors, looking only at log star neighborhood. Really amazing. You want to tell them the algorithm?
I can tell you the algorithm. I mean, if you have time.
You want it as a real, or you want to see the algorithm?
So I'm happy to tell you the algorithm because it's amazing simple.
Yeah, it's very simple.
Well,
yeah, I mean, you stop there only, so
Well, I was planning whether I should have a slide for it. Right. So basically what you do is you look on your color as a string of log n bits initially. And you recolor everyone by basically like you look on your right and you recolor the guy by you put basically like the position. So let this be let I be the first position where my color differs from the next color. And so my new color will be basically this index I plus the content of this bit. So this is some CI in here. So this is i's bit of my color. So I put here IC.
So it's a successive string. You have, since everybody has a name between 1 and n or 1 and n squared, doesn't matter. It's a log n bit coloring, and in one step you reduce the coloring to have only log n bit description. And then you repeat it, and then you look just at two neighborhoods, and then you recap.
Right. So this starts as log n bits, and this is now log n bits plus 2 or so, and you just repeat. If you think about that, you will see that it's
How standardizes naturally then.
Yeah.
right. So maybe like I'm kind of dying to ask you. So I know that like Natalina is actually involved in this work, but I think he came after like Kohl-Wishkin.
He proved the lower bound.
I know that he proved the lower bound, but I think the originally it was really like Kohl-Wishkin, and I think
They proved the upper bound.
Yeah.
So he showed that you cannot beat it.
Right.
Of course, after they did it,
Yeah.
It's all in my book if you want.
Oh, okay.
Another commercial break.
All right, thanks.